We've been looking at second quantization, which is the theory of the kinematics of many identical particles. And we've written down Fock space as the candidate solution for how to represent states of many identical particles where we don't have a definite number of particles. So there can be an arbitrary number of particles. Now, up to now, the operators of interest, the ones we've looked at, have all had the form of some kind of annihilation or creation operator. For some countable basis. So I write orthonormal basis as ONB. So we've been looking at operators on this Hilbert space here, the second quantized Hilbert space, Fock space. We've been looking at operators in terms of annihilation and creation operators, which are in turn defined in terms of a single particle basis phi mu. Now, today I want to introduce an object. It's a very convenient object that allows us to express things extremely compactly and also has some interpretation. And that object is a thing called a quantum field. So that's the task for today. What define this thing quantum field in this context of Fock space? What is it? And express things in terms of it. That's today's objective. Now, if you recall these, I'll just write out the creation operator. If you recall the creation and annihilation operators for some basis of our Hilbert space, they obey the canonical anti or canonical commutation relations. Okay, and there's a S there for spin, not spin, for statistics. Although these things, of course, are tied together. And recall, of course, we had this definition of the annihilation operator for a state for a particle in an arbitrary single particle state psi. That is nothing other than when we express it in terms of these A mu's, psi mu, and I think there's a complex conjugate here. Yes, there is. So that's the connection between all of these quantities. There's an S there to be complete. Now, it turns out we can define something. This is somehow non-local, this expression here. These A mu's, these A nu's, they're somehow non-local. I'll try and explain what I mean by that, and then explain how to define something that's more local. So each of these single particle states phi mu are presumably delocalized over some physical region. So I better give you an example. We're going to come back to this. An example of a single particle space and a basis to keep in mind, because at the moment it's completely abstract, right? Phi mu is just some bunch of vectors. So the example to keep in mind, and we will come back to this throughout today's lecture, is just a box. A box of side L. and volume L cubed. So we're working in 3 dimensions. And we're going to have periodic boundary conditions. This is the example we're going to refer to throughout today's lecture. We have a box. It's a 3-dimensional cube. It's got the same side length for all 3 sides, three dimensions. And we're going to identify each side with its opposite face. So it's, if you like, a 3-dimensional torus. Bit hard to imagine. That's why I can refer you again to the most excellent movie Interstellar for a visualization of what it's like to live inside this box. That's the single particle space, the configuration space for a single particle is a particle in a box. There's nothing, we've seen this before in your first quantum mechanics course, solving for a particle in a box, although this box is a little bit different from the one you've studied before in that we have periodic boundary conditions instead of Dirichlet boundary conditions. But otherwise, it's a fairly standard Sturm-Liouville problem to get the solution. If you solve Schrödinger's equation in the box, you work out that its eigenstates are plane wave type states. And that gives us these eigenstates are in turn an orthonormal basis. So we choose the appropriate orthonormal basis for this example are the plane waves. We'll use K here. So the role of mu is now played by K here. Mu is a label. There we go. So if you solve Schrödinger's equation for a single particle in a 3-dimensional box, side length L with periodic boundary conditions, you get that these are the eigenfunctions, these plane waves here, and they have some eigenvalue which is not relevant at the moment, which is k squared, right? You should sort of feel that in your intuitively. As soon as you see this, you know the eigenvalues of the corresponding eigenvalues are k squared. Now, I'm going to try and give some justification for what I mean by these annihilation operators as being somehow delocalized. So each of these plane waves is, well, it's precisely that, right? It's a wave. If you take the absolute value of this wave function, you get a number. In fact, you get the same number everywhere throughout the box. And that number is 1 over root v. So the probability, if you put a particle in one of these states, the probability of detecting the particle is, well, it's uniform probability distribution over the box. if you consider now A, K, which is the operator which creates a particle, be it a fermion or a boson, in this state phi k, then what it does is it creates the fermion or the boson, happily enough, and that boson or fermion is delocalized over the entire box. It's in a superposition of being everywhere in the box, which is fine. I mean, that's great if you want to construct eigenvectors of the Schrödinger equation. But sometimes you want to model a process where you've placed the particle in a definite location or as close to a definite location as possible. That's the question that we want to look at today. How would you even describe that using these kind of operators here? Well, the answer is not too complicated. I'll give the answer informally first. I mean, even at the level of rigor and normal in physics, what I'm about to write is pretty bad. It doesn't get much worse than what I'm about to write. I'm going to put big old scare quotes everywhere. Because this is as poorly defined as you can possibly imagine. I'll do it this way. AS in physics it's kind of clear, right, that if you want to put a particle at position x, then it's got to have its corresponding single particle wave function. It's got to be delta x. That's what it means to be at position x. So we know how to create a particle in an arbitrary single particle wave function. Delta x is a wave function. Why not describe the process that creates a particle at position x as the creation operator with a particle in a wave function delta x? Okay, so this is morally fine. But I hope you're aware of the difficulties of working with interpreting delta x as a wave function. And that this is not something that you really want to work with any level of seriousness, because things can go badly wrong very quickly indeed. That's why we're going to do exactly this, but slightly indirectly. We're not going to do it. We're not going to exactly define this process according to this definition here, but basically we're going to do that. And in doing so, in trying to make this thing slightly more well-defined, we'll write down something called the quantum field. I already shown you the proof that 0 equals 1 in this course? Oh, I have to show you this. This is important that you know this. Because of course it's absolutely fine in physics to work with delta functions, right? These are wave functions. We can have particles in delta functions. I don't see a problem with that. All right, I'm going to prove to you that 0 equals 1. Let's consider a particle in a position eigenstate, right? It's in an eigenstate of position. There it is. It's position x. Now, I'm going to multiply this eigenstate of position by the identity operator. Like, why not, right? So the identity times by x is x. If I take the x equals identity times x. But we know, of course, that the commutator of position operator and momentum operator, well, that's I times by the identity, so the identity is minus I times by the commutator of this thing and this thing. Now, let's, okay, this is a vector. Why work with wave functions when we can work with numbers? Let's take the expectation value of the left-hand and right-hand side in the position eigenstate, right? It's an eigenstate of position. I can ask what's the probability that the particle, the total probability that the particle is there. Well, that's 1, right? The particle's there, so there's a probability of 1 of it being there. And now, I've got this expression here. Well, I know what to do with this, right? This is just x minus I x hat p hat plus I p hat x hat. But x, when it applies to the position eigenstate, we know what that is, right? We know that the eigenvalue of the x hat operator is x. So we've got 1. And that's minus I, I'll get rid of this factor of I. And then x, this is an eigenvector of the x hat operator. So this must be x, it's the number x. X, expectation value momentum, plus I, x, expectation value momentum. But this is the same number. So is this. Oops, there's an x here. So, but I've got the same number minus each other, so that's actually 0. So for sure, 1 equals 0 in quantum mechanics. Okay. A colleague of mine once said to the first year quantum mechanics course, if you cannot explain why that is wrong, then you will fail this course. I won't go that far, but you ought to know, you ought to have an explanation ready for why that doesn't work. Does anyone have an explanation for what's wrong with this derivation? Yep.
I think P isn't properly defined when it's applied on X.
P is not properly defined when it's applied to X. That's an excellent answer. That's one way of saying what's wrong with this derivation. There's multiple things that are wrong with this derivation. That's a good one. And physically, that's the way to explain this. There's two ways to explain what's wrong here. There's a physical way and there's a mathematical way, and I think it's worth saying both. So physically, what's the average momentum of a position eigenstate? Well, according to the uncertainty principle, we know we're in for trouble, right? Because this state here represents the situation where the particle is localized at a definite position. Therefore, it has a completely indefinite momentum. So at best, this is infinity, right? And when you've got infinity minus infinity, then it's up to you where you want to set the difference between the two infinities. So that's the physicist answer, and I think that's perfectly acceptable as an answer. The mathematician's answer comes way back up here. And it says, whoa, you just said that that's an eigenstate of position. Well, that's not a vector in Hilbert space. This is not an honest resident of Hilbert space, what you wrote down there. So just the words eigenstate of position are actually wrong. Okay, so that's, but you know, be aware of why this is wrong. And that's why we have to be careful when we write things like that down. Now, one way to get out of this physically, and I think this is also extremely illuminating to do this, is to say, well, okay, I don't mean delta function of position, I just mean Gaussian. I mean a Gaussian that's highly strongly localized, right? A strongly localized Gaussian. And if you put the Gaussian in, the tightly localized Gaussian here, then you get a different answer altogether. So you should be very much aware of these subtleties. All right, okay, that's enough for this interlude. Let's take a look now at defining quantum fields, making sense of this thing in the scare quotes here. This only makes sense in the case where our single particle Hilbert space has a position. So I better make that clear. Let H be the set of square integrable functions on R3, or the actual case that we consider for most of today, the set of square, not three integrable, square integrable functions on S1, the circle, Cartesian product S1. Okay, the three-dimensional torus. That's the box with periodic boundary conditions. Then let phi mu of x be an orthonormal basis of wave functions. So now we've got this position degree of freedom. And write this. Yeah, there are two operators here. Yeah, with hats. Now these aren't quite honest operators, that's for sure. But they're almost honest operators. So they're called a psi hat of x is a thing called a distribution valued operator. I'll tell you what that means in a second. psi x by itself is not an honest operator, but it almost is. It's really a box. You should think of it as a box. What is psi hat of x? It's an unbounded operator on Fock space gamma s of h, as long as you put in a smooth, rapidly decaying function. If you put a smooth, rapidly decaying function into psi hat of x as a box, it will produce for you an unbounded operator on gamma of s of h, namely, according to this recipe here. But that's none other than that, as of f in the state f. Yes. So as a naked object, psi hat of x doesn't have, it's not not even an unbounded operator on Fock space. But as soon as you integrate it against some function f of x, it becomes an unbounded operator on Fock space, and that's actually none other than the annihilation operator in the state f. Why would we ever define these things? Well, sometimes it's a mathematical phantasm, really, the quantum field. It's something that doesn't exist, but its existence sort of pushes itself on us like the imaginary numbers do. If you want to solve the equation x squared equals minus 1, you can't do that in the real numbers. There is no solution within the real numbers. And that's the answer, right? You can't solve that equation. But in coming up with what we would think a solution might be, we come up with the imaginary number I. And similarly, the quantum field is an object like I. It's not an operator on Hilbert space. You can't think of it like that. But you often want to solve the problem of having a general purpose box that can create particles in any single particle, or annihilate particles in any single particle wave function you like f. And that box that does that is nothing other than the quantum field psi hat of x. So it's a phantasm, it doesn't exist, but we want to make sense of it and use it as though it does exist. And it's worthwhile doing this because it makes, you may have thought that it was very tidy, all this formalism with a hats and a daggers. Well, it gets even nicer when you start expressing things in terms of quantum field operators. So there's something to be gained in defining these objects. And secondly, we sort of think that they're real in relativistic quantum field theory. So, I don't know, you have to make sense of them somehow. Well, the first thing you should do when you see an operator like this is you should wonder what's its commutation relations. What happens when we compute the commutator or anti-commutator of two of these quantum fields? Well, we just insert the definition, which is still there on the board. Yep. There it is there. But we actually know what this thing is. We computed that in the previous lecture, or the lecture before. So one of these sums goes away, and we're left with one sum. Times by the identity. And that's actually the completeness relation written right there. So we have another name for this object. Delta x minus y. Now if you define quantum fields as, let me see if I still have it there. Yeah, if you define a quantum field according to A of s of delta x, and you try and compute that commutator that I just computed, then you can see that there's something not quite right with that with the bad definition, because the commutator of psi x and psi dagger of x, psi dagger of y would be something like delta squared, so that's not quite right. So this is clearly the better definition already. It allows us to compute commutators. And the real beauty of these quantum fields only comes when you start to write second quantized Hamiltonians, or Hamiltonians for many particles, in terms of them. That's when it gets really worthwhile. If you have an operator J hat so you have an operator like that, that's something that appears quite often when we're trying to describe operations on Fock space. Then it turns out you can rewrite that in terms of psi x's and psi dagger x's. So the first thing is to look at this thing here. So this is, what's this expression? Well, there's a equation for it, d cubed x phi mu x bar jx. Remember, this is a single particle operator. So that's what that thing means. It's just this inner product here, this expectation value. And that's just left alone. But that's super close to the definition of a quantum field. We just associate this guy with that, this guy with this, and do the sums, bring the sums past the integral. And we come up with that immediately. It's very beautiful. Where j of x is none other than the position expectation value of j. So this is a fantastic way to remember all these formulae that we've encountered. All you actually have to remember is how to do things in terms of single particles. Remember that whenever you put a delta function, you now have to put a quantum field, and then remember the definition of the quantum field, and you can kind of work backwards. I'll do one more example. This is a fairly general example for single particle operators. Now I'll do a very specific one. Let's consider the case where j of x is delta of x, which is not an honest operator, but you know. If you like, that's the potential of a particle which is super duper localized. And if we substitute in this into that formula there, then we define something called the number density n hat of x, which is this is called the number density. I didn't mean that at all. So this represents, if you like, the potential of some point localized defect. And the second quantized version, or the Fock-space version, or the many-particle version of this potential is represented by this operator here, which is not an operator. Okay. Remember, quantum fields are not operators, but they become operators as soon as you replace delta functions with Gaussians that are tightly localized. And there's something quite nice about the number density. The total particle number operator is the integral of the number density operator. Which I'll leave, I think, as an exercise. Will I? Yeah, I'll leave that as an exercise. Okay, that's pretty nice for single particle operators, but what about for the really nasty stuff? Like potentials between particles, multi-particle potentials. Is there any gain in writing things in terms of quantum field operators? And the answer is, not surprisingly, yes. And in fact, it's extremely nice and elegant. If you remember from last lecture, we wrote out the Hamiltonian for an interacting collection of particles. Should still have it here somewhere. I guess I will write it out. Here's the answer we got in the previous lecture. If you take the if you consider a collection of particles with a standard kinetic energy term T hat, which I'll write out in a second, and standard potential energy term V naught, which you're allowed to change, and you can allow them to interact with each other according to some potential V, then the Hamiltonian describing that situation, we wrote this out in the previous lecture, in terms of annihilation and creation operators, is given as follows. That's the full interacting Hamiltonian. Now you can actually write this in terms of the field operators psi hat. In fact, I've done the first part of the calculation already. If you let j hat be this stuff and just simply apply the result that I have up there, then we already have part of the answer already. It's only this thing here where we haven't done the full calculation yet. But it's exactly the same procedure, and so it's not even an exercise. I'm just going to write out the answer because that's what you do. There's not much else to it. Okay, that's the first term written out. I just used exactly the formula written up above. Now for the second term. So y is on the outside or on the inside? Inside, I put them. So I think that's pretty super duper, because usually it's pretty easy to remember this, and this is given to us from single particle quantum mechanics. We know what the kinetic energy term is, we know what the external potential looks like, and we know what the potential between two particles usually is. Like, it's something like the Coulomb potential minus some sort of decay factor. So I'm using mu's and u's, and how about size? So we can write this Hamiltonian here. I mean, this is a bit of a mouthful, really. Like this sums over basis vectors, and it's a fourfold sum. And it's pretty ugly. Whereas this thing here, this is super succinct and expressive. It's exactly the same object, but this one's easier to remember. You just have to remember that psi hat of x is not an operator. It eats functions for breakfast and then gives you an operator. It's the only thing you have to keep in mind. But the temptation gets very powerful once you know about the commutation relations to treat psi hat as an operator. And in fact, it works. Often enough, if you pretend that psi hat is an operator, then all your calculations just work. What I'm going to do now is consider two examples. So we're going to use these as somehow motivating examples for the rest of the course. And I'm going to tell you a little bit about the physics of these two examples. Two examples. Both examples will be gases. So this Fock-based formalism is really good for situations where you don't know the exact number of particles. So this happens a lot when you have gases. If you have a gas of particles confined into some box, then generally speaking, you don't know how many particles you've got in there. Sometimes you can count the particles after the fact, but you don't have every time you prepare the system exactly the same number of particles. There's always an indeterminate number of particles stemming from the fact that the way you trap the particles wasn't exactly reproducible each time. And that's the sort of thing that occurs when you have dilute atomic gases. You can trap the gases, you cool it down with evaporative cooling, and you know you've got some gas there, you don't know exactly how many particles. This is the formalism works very well to describe that. Another situation where this works very well is when you have so many particles, you have no hope of knowing how many you have. So that's the kind of situation when you have a metal or a plasma. So if you have a piece of metal, like the conductor in this, or like the clip on this clipboard here, you know there's some electrons in there, you know there's probably a lot of them, a large number of electrons in there, and it seems unlikely we'll ever know exactly how many electrons there are in that piece of metal. So there again, the formalism of Fock space is the right formalism to use. It's very good at dealing with situations with an indeterminate number of particles. Similarly, plasmas. You have a plasma in a fusion ring. Of course, you don't exactly know how many particles you have. Again, that's a perfect situation to describe with this formalism. And so that's exactly the two examples I'm going to cover. We're going to do, probably won't get to example 2 today. Example 1 and example 2. So example 1 is a dilute atomic gas. We'll make it neutral so that the particles are not charged. You'll see why that's important in a second. And example 2, which I'll do later, probably in the next lecture, is a degenerate electron gas. which is the kind of thing that you model plasmas and metals with. And we're going to see, and this is what's really amazing about this formalism, is that the simplest tools that we learn in quantum mechanics will give us a huge amount of insight about these very much cutting-edge, relevant physical examples. So although if both of the Hamiltonians, I mean, I don't even have to write down the examples already, because I've already written them down. If you look above, that line there, these two lines there, are the Hamiltonians for both of these examples. Both the dilute atomic gas and the degenerate electron gas, they both have exactly the same Hamiltonian. In some sense, I need not write down another equation. They have a kinetic term, that's the free particle Hamiltonian, which is always the same, minus h bar squared grad squared over 2m. They have a potential term, which is, for both of these examples, going to be just nothing. We're going to put them in a box, or constant. And they both have an interaction term. That's the difference between these two things, apart from the fact that one's bosons and one's fermions. The potential for the dilute atomic gas, it's more convenient to have that to be extremely short range. That's a better model for how these particles interact. They only interact when they're very close to each other, and so the potential is almost like a delta function. Whereas for the degenerate electron gas, the potential is more like this thing here, with psi being effectively 0. So those are the two examples we're going to cover. And we're going to learn that the tools of ordinary quantum mechanics are extremely powerful in looking at the physics of both of these examples. We're going to learn that we can treat this nasty interacting bit as a perturbation, and we can study this problem variationally and also with perturbation theory. And we'll learn a tremendous amount about the physics of these two very complicated examples, just from doing the stupidest perturbation theory and the stupidest variational calculations. And in fact, it's so good that you hardly need ever go beyond perturbation theory and variational calculations if you want, fairly good accuracy, several decimal place accuracy. It's just absolutely astonishing. So I think I'll do the dilute atomic gas first, and then I'll give you a little quick tour of how to solve that variationally. All right, so there's really nothing to do here. I'll just write down the potential, and then we've done the example. All right, what's the potential appropriate for a dilute atomic gas? Well, the first thing you can try, and this actually works rather well, sort of shockingly well, is to just approximate the potential between two neutral particles as a delta function. Like, there's no potential, no potential, no potential, no potential until they're right on top of each other, and bam. So as long as the radius of these particles is small, this is a fairly good approximation. Okay. G is some constant. Let's actually put numbers to this because we can. It's 4 pi h bar squared Na over m. Okay, we know almost all the symbols here, and there's only one we don't, little a. So m is the mass, n is the total number of particles, so this constant here depends on the total number of particles, which is kind of interesting. So this A here is a thing called the S-wave scattering cross-section, which we're going to learn a lot more about in the next part of this course, but for today is just a number. So there's some argumentation that you need to make to prove that this is a good, effective approximation to the physics of dilute atomic gases, but that's it really. There's nothing more to it. But how do you solve this? How to solve it? How to solve it? If it's super dilute, if there's not many of these particles around, then they ought to be like free particles, because if there's only 1 or 2 particles per square meter, then they hardly ever see their friends, and so you may as well pretend that they're just free particles. And then you can do perturbation theory in the smallness of G here. Presumably, right? Presumably. And that works, you can do that. But we're going to look at the absolutely other extreme where there's quite a lot of particles. We're going to use if you have a really dilute case, then you can use perturbation theory around the free particle solution. There, the wave functions are just I can even write them out actually. So I didn't ever explain how to get the free particle solution, but that should be simple to describe, right? The solutions look like Fock basis vectors, where those are what the eigenvectors of the free particle case look like. They look like states where there's a definite number of bosons in each of the eigenstates of momenta K1, K2, so on, all the way up. The denser case is much more interesting, and there perturbation theory definitely fails, right? Because we've got lots of particles all near each other, all talking. And there you should use the variational method. And to use the variational method, you need to have a set of vectors to vary over. And I'm going to tell you a little bit about a nice set of vectors to vary over. Same story can apply to the electron gas case, although perturbation theory just works a lot better in that case. Unless you have a superconductor, in which case you have to do things completely differently. And the other extreme in the metal case is the insulator. There you also would use a variational method. It's probably the best way to approach it. And I've just named all the important examples in solid state physics. So electron gases and atomic gases, you could spend your career studying these things. Because that's the stuff that makes us. Good, let's talk about the variational method. How does the variational method work? Well, you have your full configuration space, Fock space. That's this. Difficult set to really get your mind around. It's infinite dimensional. It's got lots of nasty correlated functions. It's very difficult to represent on any kind of computer. And then you take some human readable subset of that space, call it V. And this space here is something you can work with. Something you can work with. V does not have to be a subspace. V does not have to be smooth. V just has to be something you can work with. And then you do the following. You take the infimum over all states in the set that you can work with, and that gives you a number. And that number is always an upper bound to the ground state energy. And that's a simple application of the maximum principle for eigenvalues. Ground state. Now, at this point, this doesn't look very profound, right? So I've just told you that if you don't choose the right state, then you're going to get a worse energy than the ground state energy. Yep, that's absolutely true. What makes the variational principle kind of amazing is that you don't have to be particularly clever about your choice of V. You have to have some insight into the physics of the system, just a little bit of insight. You have to have some physical intuition for what the ground state should probably look like. And then when you design the V, and the V is up to you how you choose this thing, you make sure that the states that you think that the system looks like are in there, and then you let the variational principle do the rest. And what it does is it searches around this space, and it finds, you might think that the ground state looks like this, but then it actually says, oh, no, there's something even better. And then it will take you around this set until it finds the best state that minimizes the energy. And sometimes you have some idea about what the ground state energy is. You just don't know what the ground state looks like. And you can get an estimate for how sort of close this method is in terms of approximating the actual ground state energy. And the amazing thing is that it's a black box procedure that just hands you optimal answers, and it's improvable. So if you have a way of making your set V bigger, let's call this V0, V1, and so on, bigger and bigger and bigger, then this just gets better and better and better. So it's this really systematic calculational procedure. The only bit where you need some insight is in designing these Vs. You need to be a genius at that moment, but then you don't need to be a genius when it comes to actually getting the numbers out. And I'm going to introduce you to, in the last couple of minutes, a very, very powerful set, variational set in Fock space. This one turns out to give you really, it just works too damn well, this set I'm about to tell you. It's hard to come up with anything that this set can't handle. And the set in question is that of all coherent states. So I think you've met them in the exercises already. Is that true? Coherent states, were they in the exercises yet? No, they weren't. Okay. Well, that doesn't matter. So perturbation theory is the absolute no-brainer method to solving anything in quantum mechanics or indeed in mechanics. You don't have to know anything. You have to just be able to type into Google first order perturbation theory and it hands you the formula to solve. And you put in the relevant terms of your Hamiltonian and it will hand out a approximation to the first order shift in the eigenstates. Variational method is a little bit more complicated in that you have to design a good variational class, but once you've got one, it's as simple, if not simpler, than perturbation theory. And I think it's fair to say that most of our insights in physics are based on one of these two methods. They're the go-to methods for solving things in quantum mechanics. So you definitely want to get used to them, because you will see them again. Okay, let's recall the definition. So suppose we have just one mode described by a single annihilation creation operator pair A and A dagger. Then the coherent state, the vacuum state, which is also a coherent state, is defined by A applied to 0, and a coherent state alpha, with alpha being a complex number, is defined according to this equation there. Now you can regard that as a consequence of a different definition, or this definition as a consequence of this definition, and that is where we express things in terms of the Fock basis. I know there's an alpha to the end there, and I think there's a 1 on root factorial. I didn't write it out, so I'm going to have to try and remember this, see what happens. I think that's the answer. Yep, that's it. So this is the alternative definition of what a coherent state is. You can choose either or, whichever one you like. There's a third definition, which I'm going to give you, which is also a consequence, if you like, of these two. So this equation as written here doesn't make it entirely clear that this thing exists. Because A is not Hermitian, there's no rule, it's not self-adjoint, there's no rule that it has to have eigenvectors at all, let alone eigenvectors corresponding to continuous spectra. So this is, it's not clear that leads to a well-defined state, but this expression here proves that this is an honest element of Hilbert space because this series here converges as n tends to infinity. All right. I'm going to introduce yet another definition. This is possibly the most useful of the three that I'm going to show you. Using annihilation and creation operators, we're going to introduce a special operator called a Weyl operator or a displacement operator. There it is there. You can prove it's unitary. So this is like the classical exercise. The Baker-Campbell-Hausdorff formula, if you use the Baker-Campbell-Hausdorff formula on this expression here, you can show that that is equal to this expression, and furthermore that D is unitary. You can prove a zillion other cool and interesting results about this operator, but none of them we're going to use today. The only result we need today is that dA alpha applied to the vacuum state is in fact our friend the coherent state. And it's indeed this formula here which proves to you that that's correct. There's the minus a half alpha squared right there. This operator applied to the vacuum state is just the vacuum state. That's a Taylor expansion. And this applied to the vacuum state gives you that Taylor expansion there. So that's how you prove that a coherent state is just a displaced vacuum state. What else do we need? I guess that's all we need for the moment. Oh, they're overcomplete. It's pretty cool. So they're not all orthogonal, but they certainly span all of Hilbert space. Now, why do we like coherent states? Well, because we can calculate every single thing about them. We know all their moments. We know all their expectation values. We know their wave function. So they're a fantastic class of states to use as a variational class. We're not going to use single mode coherent states, we're going to use multi-mode coherent states because we've got multiple modes. So the operators we actually have to deal with look like this. So let alpha underline be just a list of complex numbers and define a multi-mode coherent state according to that equation there, which has an equivalent expression in terms of these displacement operators. And this is our I sort of overloaded the definition there, but I think that's clear. It's just the product of the displacement operators for each mode, or the sum of them, if you like. And we're not going to do it today, but we can calculate all moments of these states here. So they're very useful in terms of calculations. And the way we do that has a name. It's called Wick's theorem. Although the coherent states we have here are so simple that we don't need to invoke Wick's theorem to do this. And in the next lecture, we're going to use this class of states, the coherent states, as a variational class. To study dilute atomic gases. And shockingly, we will find that it's an incredibly good variational class that does an amazing job of explaining every single experiment ever done with dilute atomic gases. In fact, it's super hard to come up with something that it doesn't work well for. That's the story for the next lecture. Okay, thank you very much.